Superposition of pulses is really just to do with interference. Interference of waves or interference of pulses. When we're talking about pulses, we're usually talking about waves of some kind. Interference is when two or more, but we'll focus on two, when two waves pass through each other. And superposition is the addition of those two or more waves as they pass through each other. So two waves are coming together, they pass through each other. The moment that they overlap, there is superposition, or they experience superposition, which just means that the two things add together. The principle, these are all very lofty sounding. It's really not this hard. When I start drawing pictures, you'll understand it. But the principle of superposition is the resultant displacement of the medium that we're talking about is the sum of all individual displacements at that point. All right, just kind of note that, and then as we go through this, it'll make sense. So constructive interference is this. Let's say both waves, so let's imagine that this line, this first line right up here at the top, imagine that this is like a slinky, a long spring. It could be a rope or an elastic band or something like that, as long as it's not pulled too tight. Imagine it's stretched out, and I'm holding it at this end, and somebody else is holding it at this end. And what I'm going to do is I'm going to flick my hand up and back down, and that's going to create this pulse, and that pulse is going to move away from me. Okay, so if we ever talk about a pulse, this is like a peak or a crest or a pulse or a part of a wave, something like that. Let's throw a number on here. Let's say that this thing is 20 centimeters tall. And let's say at this end, somebody else does the same thing. And let's just purposely choose a different number just to make it kind of easy to talk about. Let's say their pulse is only 15 centimeters tall. And the two pulses are coming together. Okay, so as the two pulses head towards each other, there's going to be a moment somewhere in the middle. I'm going to do it here. There's going to be a moment of overlap. Okay, so this just happens for a quick moment. So let's just say here, moment of overlap. That moment of overlap is where constructive interference happens, and you could say that's where they experience superposition. Okay, so if this wave here, this pulse is 20 centimeters and this pulse is 15 centimeters, what we said in our previous thing is the principle of superposition basically says it's the sum of those amplitudes. Okay, so what we're going to get here, just for a moment, is the two waves are going to overlap momentarily, and we're going to add together their amplitudes. So this 20 plus 15 is 35 centimeters. What we're going to get is we're going to get this pulse that is 35 centimeters tall. But just for an instant, because remember, this 20 centimeter wave is going this way. It's going to continue to go that way. This 15 centimeter wave is going to the left. It's going to continue to go to the left. Okay, so after this sort of superposition happens, this 15 centimeter pulse is still just traveling to the left, and the 20 centimeter pulse is still traveling to the right, unchanged. Okay, so the 20 centimeter one was going to the right the whole time. It's here, it's going to the right, it just continues to go to the right. That's what we'll show over here. It's just for this one instant, this one moment where the two waves kind of overlap. And I have an animation in a second, and you can kind of see that. This is constructive interference because both pulses are on the high side, or I don't know how you'd say that. Both pulses are on this side. Okay, let me write this in a different color. Both pulses are on this side. What you could kind of say is, let's say anything on this side is positive, anything on this side is negative, for example. We have constructive interference because they're both on the same side, they're both positive, they're both going to add. If they were both negative, they would still add. I would just get something on the negative side, something bigger on the negative side. But what if one is on the high side and one is on the low side? What happens then if the pulses are pushing the medium in the opposite direction? So for example, one is on the high side like this. Let's again go 20 centimeters. And it's going this way. And I've got one, again, 15 centimeters. It's on the low side. We could imagine, again, anything this way is positive. Anything that pushes it this way is negative. So if they push the medium in the opposite direction, so again, one up and one down, the result is going to be these smaller waves. It is still superposition. Okay, so they're still, adding together, but when we add them together, I'm going to get positive 20 plus negative 15. I'm only going to get 5. What I end up with then is this little tiny pulse in here, 5 centimeters high. Again, there's my smaller waves, right? So destructive interference results in smaller waves. They don't have to be on the positive side, right? If my 20 centimeter wave here was on the negative side and my 15 was on the positive, this little 5 centimeter wave would actually be going down instead of up. Okay, so it doesn't matter which side. It's still called destructive interference. At the end of the interference, though, this 20 centimeter wave is still traveling to the right, unchanged, so still going this way. The 15 centimeter one, I forgot that arrow, but it's going to the left. It is still going to the left. It's over here. So still going this way. So the two waves, they meet in the middle, and momentarily when they overlap, they add or subtract to something bigger, but then the two waves just keep going. And if you're kind of having trouble picturing that, let's imagine this. Let's see if I can get this to play. Here it is. So here's my two waves, and you can kind of see them. We pause just momentarily. Up here on the top, what we can see is here's a single wave on its own going to the right. Here they're drawing a single wave on the left, a single wave going to the left. It's down here where we're going to see if the two waves were together, what's going to happen. And you can kind of see if I hit play, it's going to start again. As the two waves come together in the bottom, right there. So right for a moment, they overlap and you get something bigger. So let me see if I can pause it. I kind of missed, but you can kind of see what's going on. If we kind of go down, let's say this line right here, you can see this guy is just about 2 squares tall. This guy is maybe 1.5 squares tall. If I add 2 plus 1.5, I'm getting 3.5 squares tall. And you can download the note and try this on your own. If I could pause it like right over here, I think they would go up to 4 squares tall. But this right here is the constructive interference. But it doesn't stay like that. Sometimes people ask, is it permanent or whatever? Nope. You can see the two waves overlap, and then they just carry on unchanged as if they never saw each other. Here's destructive interference. Same setup. We've got two waves, one on the top, one in the middle, but it's the bottom one down here where the destructive interference happens. So the wave up here is on the high side, the wave here is on the low side. It's this bottom one here where the two waves are going to meet and overlap. And let me see if I can pause this guy. Well, kind of. If I go down this line right here, this wave is 2 squares, let's say on the positive side. This wave is about 2 squares on the negative side. Right here, it adds to 0. Or basically 0. It's just off because this one's just off, but basically 0. But you can still see over on this line, we do still have some interference happening. This guy is maybe just over 1.5, 1.7 or something. This one is maybe negative 0.2, something like that. I get about 1.5. Again, not permanent. Whoops. Here we go again. It's not permanent. They meet, they overlap momentarily, and then the two waves just carry on unchanged. Nodal points. Sometimes you get these specific points that as that interference is happening, there's a certain point that just never moves. And that's called a nodal point. It remains at rest. And if we were in person, I would demonstrate. We can do this with slinkies. I usually do this with a guitar string to show you. If you play the guitar or some other stringed instrument like that, you may have heard of nodes. Anyways, nodal points remain at rest throughout the wave interference. There's also something called refraction. And if a wave enters a new medium, then it's going to change speed. It's either going to speed up or slow down. That speed up or slow down can cause a direction change. It definitely causes a speed change. But here's something to notice. The frequency remains constant. I don't know what happened over here. Somebody sabotaged my notes, but the frequency remains constant. Let's check it out. We've got a wave on the left-hand side over here. It comes in and it's going really fast. Let's imagine this is like, a really light, maybe a plastic slinky. This one over here is a much heavier, thicker metal slinky. And I tape the two slinkies together and I send this pulse down this way. It comes in on a fast medium and then it enters a much slower medium. And you can see the speed change. Let's focus on that for 1 sec. You can also notice that there's a bit of a direction change. This is, if you remember from optics in grade 10 science, this is called partial reflection, partial refraction. That's what we would use for light anyways. What that means here is part of it goes forward, but part of it reflects backwards as well. Okay, so there's a bit of a direction change. The frequency here would remain constant. If you could kind of, I don't know, put your finger over here and count how many pulses pass your finger per minute, you would get the same number of pulses passing your finger over here per minute. You'd say, but over here they're going much slower. Yes, they are, but they're also going to bunch up over here. They're going to be much closer together. Over here, the waves are going to be more spread out. Frequency remains constant. This is going from a fast medium to a slow medium. Similarly, if I go from a slow medium, so the thicker, heavier slinky, going to a fast medium, you can see how the wave, it's something interesting to notice is the amplitude gets bigger. So you can see the wave gets bigger because it's easier to push that light slinky. It goes faster. Again, there is some part of the wave that reflects back and some part of the wave that just keeps going forward. Diffraction is the spreading out of waves. All right, so we're going to demonstrate with this. If this will work, let me see if I hit play. No, oh, it doesn't work. You may have to try to download the node and try this, but what we're talking about here is the spreading out of waves. So this opening right here, if you can imagine, this is like some kind of a wall, and the green are waves, and they're traveling down this way. When that wave hits the wall here, it's not going to go through, but the part in the middle here is going to go through. The part at the edges, because of friction, is going to kind of curve a little bit. So it's going to slow down a little bit on the sides, and we're going to get a bit of curve. That is diffraction. And normally, I can actually grab this little slider over here, and you can change it. You can pull it down, and that'll change the size of the opening. And we'll see we actually get more diffraction. Let's see, I don't think it's anything to do with that. No. Too bad. Anyways, it's good little animation, and if you can try downloading it, try it on your computer. It may work. Anyways, if the opening is bigger, so this opening right here, if the opening is larger than the wavelength, then we get a small diffraction. If the opening is smaller, then we get a larger diffraction. There's some happy homework for you guys. We're always the Orange Book, so that's good for